Imagine your signals sailing into the atmosphere, bouncing off invisible layers high above Earth, and then returning to the surface thousands of miles away. That is the essence of skywave propagation, a phenomenon that makes HF a gateway into global communications. By understanding how factors like solar activity, time of day, and atmospheric conditions influence this bounce, you can choose the optimal bands and timing to reach even the most elusive stations. Mastering these concepts does more than sharpen your technical skills. It expands your ham radio horizons, transforms your on-air strategy, and turns every long-distance QSO into an unforgettable journey. Turn your ideas into reality with PCBWay.com. Enjoy high-quality PCB manufacturing and assembly services that deliver exceptional value. With fast turnaround times, reliable global shipping, and expert support, PCBWay.com is your trusted partner for every project, big or small. From prototypes to full production, PCBWay.com helps you innovate with confidence. Visit PCBWay today and bring your vision to life. Skywave propagation is a critical phenomenon for amateur radio operators, providing the ability to communicate over vast distances by utilizing the ionosphere. Without this, HF communication would be limited to local areas or ground wave paths. This discussion aims to expand the basics of this phenomenon, dive into ionospheric layers, discuss how conditions vary, and provide strategies to optimize HF communication. By the end, you will have a robust understanding of this essential aspect of radio operation. The ionosphere is a key component of HF communication, created by the ionizing effects of solar radiation on the Earth's upper atmosphere. This region allows for the bending or refraction of radio waves, enabling long-distance communication. The ionosphere comprised of layers D, E, F1, and F2. These vary in density and function. These layers are dynamic, influenced by solar activity, time of day, and other factors, which means their behavior directly impacts radio signal propagation. The D layer is the lowest region. It primarily absorbs low-frequency HF signals during the day, making lower bands like 80 and 160 meters difficult to use. At night, it dissipates, reducing signal loss. The E layer occasionally reflects HF signals, aiding in mid-range propagation, and can experience Sporadic-E events that enhance VHF range. The F layer is the most important for long-distance HF communications, as it refracts signals back to Earth. During the day, it splits into F1 and F2 layers, with the F2 layer being the primary driver for global HF propagation. This is a slide that I created that depicts these different layers. Now, the heights of these layers and the thickness is dynamic and will change depending upon conditions. On the left-hand side, you can see the F1 and F2 layers. And then on the right-hand side, at night, you can see combining these layers into a single F layer. The E layer remains consistent night and day, and the D layer, which exists during the day, dissipates and disappears at night. In the center, at twilight, between day and night, and then again between night and day, we have something that's called the Greyline, and we'll talk about that as we go through this presentation. When radio waves travel upward, they interact with the ionosphere's layers, bending as they pass through regions of varying electron density. This bending or refraction is influenced by the wave's frequency and angle of incidence. The critical frequency is the threshold below which signals refract back to Earth, rather than escaping into space. Beyond this, operators rely on MUF and LUF windows to select variable frequencies for communications. These principles form the core of long-distance HF propagation. In HF propagation, three key factors shape signal behavior. Incident angle determines how a radio wave interacts with the ionosphere. Steep angles result in shorter hops, while shallow angles enable long-distance skips. The skip zone is a gap between the end of a ground wave and the first ionospheric refraction, an area where no direct reception occurs. Backscatter occurs when signals scatter unpredictably off of the ionosphere, sometimes allowing reception beyond expected coverage. Understanding these concepts helps operators optimize signal paths and avoid coverage gaps. This is a diagram that I created that shows the sun charging the ionosphere. You can see two operators, one on the left and one on the right. For skywave propagation, our signal takes off at what is called the incident angle. The more acute or obtuse that angle, the longer the skip distance. You can also see that I've highlighted ground wave propagation, and this is when your signal travels across the ground for short distances. As discussed in the last slide, the distance between the ground wave termination and the incident angle refraction is called the skip zone. HF propagation is constrained by the maximum usable frequency, or MUF, and the lowest usable frequency, LUF. The MUF represents the highest frequency that the ionosphere can refract back to Earth, changing with solar conditions and time of day. The LUF is the lowest viable frequency for communication, limited by factors such as D-layer absorption and signal-to-noise ratio. To ensure optimal communications, operators must choose frequencies that fall between these two limits, balancing ionospheric conditions and atmospheric noise. Frequencies above the MUF will pass through to space, and frequencies below the LUF are absorbed by the D-layer. I got this image from a website, propkc2g.com. On that website, you can find various charts and diagrams that show atmospheric conditions. In this particular one, we take a look at the MUF, the maximum usable frequency. And you can see areas on the Earth where these frequencies are highlighted to let you know which frequencies would work best from a maximum standpoint for communications with other places along the Earth's surface. Skywave propagation is profoundly affected by solar and atmospheric conditions. During periods of high solar activity, the ionosphere becomes more ionized, enhancing the F2 layer's ability to support higher frequency propagation. At night, the D layer dissipates, reducing absorption and enabling better propagation on lower frequencies. However, geomagnetic storms caused by solar flares and coronal mass ejections can disturb the ionosphere, leading to erratic signal behavior and interruptions. Skywave propagation occurs in various modes, enabling diverse communication ranges. Single hop propagation allows for distances between 500 and 300 kilometers with one refraction off the ionosphere, ideal for regional communication. Multi-hop propagation extends this capability by allowing signals to reflect multiple times between the ionosphere and Earth, enabling intercontinental coverage. Specialized modes like Sporadic-E and trans-equilateral propagation provide unique opportunities for specific frequency ranges and geographic alignments. Sporadic-E propagation is an unpredictable but highly effective mode of radio wave refraction, caused by temporary dense ionization patches in the E layer of the atmosphere. Unlike normal E layer behavior, these patches can support refraction of signals in the 10 meter or 28 megahertz and 6 meter 50 megahertz bands, sometimes extending higher into VHF. These events occur seasonally, peaking in late spring and early summer, with secondary activity in winter. While unpredictable, Sporadic-E offers exciting short skip communication opportunities, often covering distances from 500 to 1,500 kilometers. Greyline propagation occurs during the transition between night and day, enhancing long-distance HF communication. This happens because the D layer, which absorbs low-frequency signals, disappears quickly at twilight, while the F layer, responsible for long-distance refraction, remains ionized. As a result, signal travel much further with reduced attenuation. This effect is strongest on 40 and 80 meter bands and is widely used for DX or long-distance communication. Understanding and leveraging Greyline paths can significantly improve amateur radio operations. This is an image that I got from VOACAP. You can do a Google search for VOACAP and use this powerful tool as a predictor of communication and scheduling. This map, which actually depicts the continents on Earth twice, has the gray line visible. That is the dark patches or nighttime shadows on the Earth. The edge of this gray line is called the terminator, and it represents what we call twilight, the transition from day to night, and then again from night to day. In most cases, both stations benefit the most when they are on or very near the terminator, sunrise and sunset line, because that's where the D layer, the main absorber of HF signals, is minimal, but the higher layers of the ionosphere remain energized. Essentially, if you're in the Greyline zone, and the station you are trying to reach is also in or near the path of the Greyline zone, you have the best shot of taking advantage of this enhanced propagation path. It doesn't have to be exactly on the terminator for both stations. There's a window before and after local sunrise or sunset when propagation can be especially good. That window can vary, sometimes up to an hour or so on either side of the actual sunrise-sunset. Stations slightly past or ahead of the Greyline can still experience improved conditions if one end is near the Greyline and the other end isn't too far removed. Overall, the greatest Greyline benefit occurs when both ends are in twilight, but propagation near the terminator can still exist beyond that narrow band, especially in the lower HF bands, 160, 80, and 40 meters, where the D-layer losses are the biggest factor. Lots of ham radio operators will use directional antennas, such as Yagi's, and point them in the direction of the Greyline terminator, and this guarantees the most successful coverage of Greyline propagation. Disturbances in the ionosphere caused by solar and geomagnetic activity significantly impact HF communication. Solar flares emit bursts of X-ray radiation, causing sudden ionospheric disturbances that can lead to immediate signal blackouts. Geomagnetic storms, often followed by coronal mass ejections, disrupt the ionosphere's electron density, resulting in unpredictable propagation. Amateur radio success depends upon strategic station design and operation. Antennas play a vital role. Horizontal options like Yagi antennas provide directional gain, while vertical antennas are better for low-angle radiation, ideal for long distance. Selecting appropriate operating modes, CW for weak signals, single sideband for voice communications, or digital modes like FT8, ensure flexibility in varying conditions. Higher power output improves signal strength, particularly during poor propagation conditions. Timing operations with known band openings further optimizes communication success. In conclusion, skywave propagation is a remarkable blend of atmospheric science and electromagnetic physics that enables long-distance communications. By understanding the roles of the ionospheric layers, like D, E, and F, operators can better predict and harness HF propagation. The dynamic nature of the ionosphere, shaped by solar activity and geomagnetic disturbances, necessitates adaptability and informed decision-making. With modern tools and technologies, amateur radio continues to thrive as both a practical and scientific endeavor, bridging continents and supporting advancements in ionospheric research. That's going to wrap it up, and I would like to say thanks for watching, everybody. If you have any questions, comments, suggestions, or recommendations, go ahead and post them below, and I'll do my best to respond. As always, thanks for watching.